All right, thanks everybody for coming today. Really nice to see so many people here. Really appreciate this is a fun joint Sizzle CGD talk. And just as a way of brief introduction, so Brian Medeiros and I are going to give a little bit of a background on CGD's focus in at the kilometer scale runs. Brian's going to talk a little bit about the science. I'm going to bore you with some numbers about the software and some of the background there. And then we're going to give most of the time to Orhan, who leads the efforts in Sizzle on GeoCat and UXarray to talk about how we can look at analyzing these runs. Like, it's great to now have a science capability. We'll talk about that, but it's kind of useless if you can't analyze it. And this all is being done today as part of a lead into, there's a kilometer scale hackathon coming up next month. And if people are interested in joining, I think we have 1 week left to register. And so we really want people to sign up if this is of interest to you. We have the ability, as you'll hear about, to look at some of this data with Jupyter notebooks, and we just really want to start figuring out how we can do this better. So hopefully this will lead to a lot of questions from you guys and a lot of feedback as to how we can do this better. And yeah, I'm going to get started and hand it over to Brian Medeiros to begin. So. I'll take it. Do you want that, or do you want?
Yeah. Whatever you want me to
Whatever
use.
is easy.
Okay, so I'm going to lead in with an introduction to just the general setting of kilometer scale modeling and a little bit of the history of kilometer scale modeling first. And so when we say kilometer scale modeling or storm resolving modeling or convection permitting modeling, we're really talking all about the same thing. Those are synonyms at this point. And what they're supposed to indicate is usually atmospheric only models, usually, well, in this case, only global. And we're talking about horizontal grid spacings of 5 kilometers or less as a general rule of thumb. And the idea is that as you get down to those scales, you start to be able to resolve updrafts, convective updrafts and convective storms in a way where you might not you might not need to have a convection parameterization anymore. And that's a paradigm changing kind of change in the way we think about global atmosphere modeling. And it started, like the first examples of these go back to 2005 with the NICAM group in Japan, who initially produced an aquaplanet simulation shown down here at 3.5 kilometer grid spacing. And then they follow that up with these simulations on the right in 2007 with realistic geography. So that's 20 years ago, and at this point, like it's quite a revolutionary change in modeling, because at this point you could easily read the literature and hear people referring to 1 degree climate models as being high resolution. So I mean, these are not climate runs; these are short demonstration runs, but it was showing the capability. And the NICAM group was really at the forefront of this. They were the leaders. They were the only ones doing this for the first few years. By 2013, they were able to show the first sub-kilometer global simulation, 870 meters grid spacing. They've continued to push the boundaries of resolution. So I think last year I was at a talk where they showed 220 meter global resolution. Again, these are demonstrations. These are very short simulations, but they're demonstrating the capability. During the 20-teens, more modeling groups became interested in pushing the boundaries of resolution, going to these kilometer scale simulations. By 2016, ECMWF introduced the HRES product. So that's a 15-day operational forecast at 9 kilometers global grid spacing. So there was one ensemble member at that point. As more groups got their models developed, by 2019, there was this diamond intercomparison, the first intercomparison of global storm resolving models. They collected 8 models at sub 5 kilometers and 1 model that was a little bit coarser to start from the same initial conditions and do a 40-day run. It was a northern hemisphere summer case. And then they followed that up in Diamond 2 in 2020 with a northern hemisphere winter case. And again, those start all the models from the same initial condition, run for 40 days. These produced enormous data sets that have been analyzed ever since then. So the last 5 or 6 years, they've been being analyzed. And we've been learning a lot about global storm resolving models and what they're capable of. Since then, in 2023, ECMWF moved their entire 15-day forecast, their operational forecast ensemble, from 18 kilometers to 9 kilometers. So we're at the point now where global operational systems are verging on this kilometer scale kind of capability, and we're pushing ahead with these like sub 5 kilometers to see what happens. Last year, the Diamond 3 protocol, sometimes it's called the Sendai protocol, was published. So what they're doing now is asking for more models to participate, and the protocol is for a 1-year atmosphere simulation, so resolving the entire annual cycle. And this is going to produce a new and gigantic data set, and part of the motivation for the global hackathon that we're organizing next month is to take a look at these simulations. So we will have access to some of the early simulations for this Diamond 3 project. And at the same time, more ambitious modeling capabilities are being demonstrated. So NextGEMS this year has a paper, or maybe a couple of papers out, that show coupled configurations, ocean atmosphere configurations at less than 5 kilometers for multiple years. So we've moved in the last 20 years from these demonstration projects with one model to multiple models being able to run to now multiple years, and now coupling capabilities becoming available. Of course, with these models, there are a lot of work. They're very computationally intensive. They take a lot of resources, and there's a lot of skepticism, I think, that I've heard from the climate community asking whether we get anything from them. And I just wanted to show a couple of slides indicating that I think that there are some things that we have that potentially provide things that we want from the climate scale, where we can have improvements from global kilometer scale modeling that will translate to improvements in long-term simulations. One of them, you can go back to the basic physics of the circulation, the equations of motion, and people have been looking at this for a long time. If you just go down to very small scales, you have non-hydrostatic vertical accelerations. And that changes your global circulation when you go to these small grid scales. So this is an example from a paper that showed four versions of a model that have non-hydrostatic effects included, and one version that uses the primitive equations with a hydrostatic approximation. What they show is that if you run these models at large grid spacings, 100-kilometer grid spacings, they all show identical solutions or indistinguishable solutions. But as you go to very small grid spacings, they diverge. They show different solutions in the large-scale circulation. So this is the zonal mean, zonal wind, for example, just indicating that when you go to these small scales, you do have effects that are affecting your large-scale circulation. That kind of generalizes, but is less easy to show in a clean and consistent way when you go to a model that has more sophisticated moist physics. So this is one example that does show it, I think. It's using impasse as a forecast model, doing 1 month-long forecasts in 4 case studies, and comparing a 15-kilometer version of impasse to a 3-kilometer version of impasse. And what they find is the 3-kilometer version of impasse has a better forecast skill out to the extended period of 2 and 3 weeks. And their reasoning is essentially what you'd expect, which is you're resolving these small-scale storms, and you're getting the life cycle of those storms better, and that's allowing some persistence in your forecast skill. Not persistence, that's the wrong word. You're allowing more forecast skill into the extended range. And the inference from this is that but if you're representing these storms better in general, you're pushing their forecast skill out to weeks. You're also going to impact your large-scale climate simulation. We have some indications of this from the simulations that have been done so far, and what it really boils down to is that when you are getting down to kilometer scales, what you're doing is resolving those convective motions, and they're coupling with the phase changes of water that are important for the heating rate, and that dominates the life cycle of these organized convective storms. So what we're finding, or what the literature is finding, is that you get these convective storms, and their upscale effects are being captured in your large-scale perspective. So, for example, mesoscale convective systems, when you represent their genesis and propagation, you end up with a better diurnal cycle of precipitation in the central U.S. or even over the ocean, for example. Similarly, when you resolve the embedded convective elements within atmospheric rivers, you get their precipitation and intensity and their evolution improved, including their vertical structure, which is shown down here. And this improves the forecast and then the representation of atmospheric rivers, and atmospheric rivers then have an effect on the water vapor transport out of the tropics into the extratropics. And similarly for tropical cyclones, if you go down to convection perturbating scales, you're actually starting to resolve some of the interior dynamics of tropical cyclones, which then have upscale effects through things like meridional heat transport. But of course, these models come with a lot of challenges. I break the challenges down into three basic categories. One is compute. You need a big computer and you need code that runs on the big computer. Brian will talk more about this. Then you need a data strategy because the output from these models is enormous, and you need to be able to manage it and store it in some kind of efficient way where you can read it. And then the third thing is the analysis of that data. And you can imagine that this becomes hard because maybe a single model field might be as big as your entire laptop's memory. So that becomes challenging, and so you have to start thinking about different tools and different workflows. And that's just one of the things that Orhan's going to be talking about. And it's one of the things that we're going to be trying to develop at that hackathon is workflows to try to start looking at these large data sets. And along the way, of course, your data management and analysis approaches will depend on your application. Weather and climate might have different requirements. And another application that's emerging for these models is training AI and machine learning models to make emulators to reduce the amount of compute that's necessary to run at these kinds of scales. And of course, you also have continued model development because even when you go to 3-kilometer grid spacing, your model's not perfect. There's still a lot of biases to deal with. So at NCAR, we have a number of projects that are trying to take steps towards these storm resolving capabilities. I'm listing 3 of them here. There might be more, but these are the 3 that I know about. Earthworks, which is led out of CSU by Dave Randall, is using impasse as a dynamical core in the atmosphere coupled to the CAM physics, coupled using the CESM infrastructure, but bringing in the impasse ocean and ice to do coupled climate modeling. NSF Storm Speed is a project that's led out of the University of Michigan by Christiana Jablonowski. That's a different approach, but similar. Basically, instead of the impasse dynamical core, it's borrowing the Department of Energy's version of the CAM spectral element dynamical core that's been reformulated to have non-hydrostatic capabilities, coupling that into CSM. That's just going to be, it's just like another die-core in CAM, so no coupled modeling is part of that project at this point, but they're planning to have convection permitting simulations in the next couple of years. And then SEMA, which is this kind of agglomeration of projects across NCAR, but that has a lot of overlap with Earthworks in terms of its high resolution capabilities, and in particular the impasse CAM configurations. All of those projects incorporate in some way trying to build intuition and experience with high-resolution climate modeling by using regional refinement. And this is just a reminder that we've been doing this for a long time with the CAM SE configurations, and in the last few years, we've been trying to move toward higher resolutions. So on the left side of the screen, a few examples going down to 14-kilometer grid spacing in regions, and then on the right, Patrick Callahan's South American configuration that go down to 6 kilometers. We can do the same thing with impasse, and we have been doing that. So these are just some examples using SEMA and Earthworks configurations from Xingying Wang's work, looking at the Western US refined down to 3 kilometers, and the maritime continent also refined down to 3 kilometers in CAM impasse. And then in M-cubed, Rosie Rios-Barrios has been doing a lot of work, and then there's other work associated with the impasse standalone model, looking at, in this case, an aquaplanet configuration where the extratropics is 15-kilometer grid spacing and the deep tropics is 3-kilometer grid spacing. And here we see a lot of interesting tropical wave behavior, as well as these emerging storms like tropical cyclones, squall lines, mesoscale convective systems. And we've also taken steps towards this global convection permitting or storm resolving modeling. So impasse is one of the diamond models, as Falco has been doing that in M-cubed along with Rosie. And this is an example of their analysis of the standalone impasse configuration. And then just recently, Adam, as part of SEMA and Earthworks, has been running CAM impasse within CESM at 3.75 kilometer global grid spacing. And at this point, I will turn it over to Brian to talk about how we got to this point and why it's hard.
All right, I always like to look at the numbers because they horrify me and impress me at the same time. So this is a comparison we did with 120-kilometer, our word salad. This is the CSM3 atmosphere land with greenhouse gas, MAM4, so 58 levels. And if you look at this, out of the box, we can run this in a CAM impasse configuration on 4 nodes. The 3.75 kilometer needs 480. It's a pretty big run. Cores, we're running on 38,400 for the 3.75 kilometer. Grid cells, there's a factor of 1,000 difference there. That's a big thing. And the time step, there's another factor of 36. So when you look at the core hours, and you see it's 2,400 for a model year with the 1 degree, and it's 71 million, well, at first that is, again, staggering. But then you look at the math, and you're like, okay, well, we have 1,000 times the grid cells and 36 times the time steps. It should be 36,000 times. So this is actually quite impressive. We're actually doing better than you would expect from a linear extrapolation. It's still horrendously expensive, and I still want a bigger supercomputer to do these things on. But this is really pretty impressive. It shows we're not hitting any scaling issues. There's a lot of things we can get into on why that's the case and why we're getting, super linear efficiency. But it's just a good litmus test, as this is a new capability. You say, aha, like if we were running 3 times slower, we'd have a problem. We're not. This is good. It's a usable case. The one thing I'd mention here, because I'll touch on it later, is if you do the math on this, not that I expect people to do it in their head, but 38,400 divided by 480, you get we're using 80 cores per node as opposed to 128 cores per node. Why is that? Well, it's because these require so much memory, and there's a lot of overhead in the memory that we literally can't push it higher. I tried 82. Doesn't work. I tried 81, doesn't work. We're at that limit. We're using 233 gigabytes per core. So this is a pretty neat thing, and improving that is something that we're gonna look on. But the key takeaway is we can run efficiency, we can scale out super linear, which is great. At the bottom, I'll point out, we talked about the output scale. So output is a function of the grid size. So output scales with the square of the horizontal resolution. So just to think about it, if it's you're going to have 1,000 times the output. So if you did a run before and it was a terabyte, you would need a petabyte. This is just what we're talking about here. Performance is roughly the cube of that difference because of the time step as well as the horizontal resolution. So again, really, really complex, large problems. A lot of developments got us here, and again, from the various teams involved in these. I was just going to highlight 3 across different areas. I can't highlight them all. On the left, this is one of the first ones that got us there. When we first tried these problems, we would submit a run we were playing on tax system and on derecho, and you'd wait about 3 hours and it would time out. And it wouldn't even get to time stepping. And we're like, well, dear God, why? Well, it turned out there was an issue in the initialization that had, it was scaling with the square of the number of processors. So you see here in the blue line, as we go from 8,000 to 131,000, this one call of this that's called many times, it was taking longer and longer. The red line, which I used to show this plot, and I didn't increase the bar size. I had to do it so people could see it. This is now flat. This was a really great effort with thanks to the ESMF team. So this is Ann, Dan, Bob, and Gerhardt, and just a really, really awesome thing. Now, we can initialize what took 3 hours, takes about 4 minutes for an Aquaplanet run. It's great. I/O, so Jim did some great work where we improved the I/O performance. I'm using the conservative estimate here of greater than 4x. I had 2 numbers. We didn't look too much. We didn't carefully benchmark this, but we had 2 numbers of 7.2x and 4.1x. So I'm just saying greater than 4x. It's still good no matter what. We also had a fun issue with a 32-bit issue. So just by way of background, when you do the numbers on these, this 3.75 kilometers, 42 million cells and running at 58 levels. You multiply that out, and you get 2.4 billion individual data points for a grid. Well, anybody who has dealt with 32-bit numbers knows that 2 to the 31, greater than 2.1 billion, you're going to have issues. And sure enough, there's a QSort call deep in the middle of this that's a C standard library call that only returns a 32-bit integer. We were subtracting 2 64-bit integers, and in 300 out of those 2.4 billion entries, it got it wrong because it was an underflow or overflow. So this was another great fix that took a while. And then on the science side, this is a chart from Peter Laritzen looking at another really rare thing. So it turned out there was a pressure level, I'll call it inversion. He'll probably say there's a much better way to put it, but at the lowest level, sometimes the pressure values weren't correct. This happened in his run 208 times over a 2-day run, which is 3,456 time steps across those 42 million columns. So not common, but enough to cause the model to blow up. So there's been fixes to that, other fixes on the physics, other fixes on chemistry. So we've had help from all sorts of from people here. I'll specifically call out Adam, who I saw is in here, and Peter, Bill Skamrock, and Danny Leung for all their help on this, getting this going. Okay, I always like to reiterate that when we have something working, that's the starting point. It's like getting a black belt. You know, if everyone thinks black belt, you're awesome. No, it means you're starting. So I call this base camp. We have the initial capability to do these kilometer scale runs. We have a laundry list of things we didn't solve. I'm not going to go through all these for the sake of time because this is not the key focus here, but I'll point out one that's kind of fun. I'll point out two. The land model initialization, as I mentioned, the memory is a big thing, and John Dennis from CISL already identified about a 20 gigabyte per node savings we can do by changing how we initialize the land. So that will allow us to up that from 80 to maybe 96 cores per node. We get more performance. Great. Luster versus GPFs, this is the one that confuses me. We can't write to our Luster file system. This is clearly below the level of the code. We write to campaign store, but the same thing just hangs on Luster. We don't know why. We're going to try on a different system, see if it's something tied to Luster or our environment. Lots of odd things. Finally, I will mention the Diamond 3 proposal. So Brian talked about Diamond 1 and 2. Diamond 1 started in 2019. We're doing the Diamond 1 runs essentially now. We're doing Diamond 2 now. Diamond 3 started just last year, and we have a proposal in that we're hoping to bring us up, rather than us being 5 years behind, we're going to be right up there with the other models in doing this as well. Also, as a big picture, there's some of the high-level folks are working on a cross-NCAR kilometer scale strategy. So that will unify a lot of these efforts in the near future. Here's my little bit of fun. I don't know how many people know memes. I am not very clued in, but I ran this by two people here who are much smarter than I am. Leading into Orhan's talk. So we have this capability to run now. How do we analyze it? And the question is, well, okay, we have these CAM-FE grids, we have CAM-SE, we have CAM-MPAS, and we don't want to write different notebooks for each grid. That's just terrible. You know, how you'd have to do all sorts of gymnastics to get it combined. So, hey, what if we can have one notebook that works for all grids? And this is the idea behind UXarray. We're really optimistic. There's some work to do, but we think we can get there. And on that note, I'm going to end this. I'll turn it over to Orhan. Are there any questions first for Brian or I? If not, we'll move right ahead and save all the questions till the end. Great. Thank you.
Did you write a time bite? How much did you write?
Oh, I'm not even checking. Yeah.
You moved it to scratch,
Thank you, Brian. Thank you for the meme as well. I think it serves very well for the transition because it connects well to a lot of things UXarray tries to do. So for those of you who don't know me, one more time, I'm Orhan Eroglu. I am working in CISL TDD, and I am leading the GeoCAD software team, and I'm also leading the software development efforts for UXarray as part of Project Raijin. So UXarray is trying to support the analysis of native kilometer scale unstructured grids in Python, coming from several grid model outputs, and doing this while extending the Xarray. And behind UXarray software tool, we have our NSF award, which is called Project Raijin, led by NSF NCAR and Penn State. And also we have been informally collaborating with DOE's Argonne National Lab and UC Davis and their SEEDS project. And you can see a lot of folks from those institutions as well. Before maybe jumping into UXarray, I'd like to introduce you one more time the GeoCAD team. So we are a small team of 6 software developers from backgrounds, diverse backgrounds. You have probably heard a number of these tools, GeoCAD Comp, GeoCAD Examples, and GeoCAD Viz, which are including many, but not necessarily all, NCL functionality to support Earth system science workflows in the scientific Python ecosystem. You have heard just most recently during last month's CGD exchange from Anissa on GeoCAD applications as well. Today, we will be purely looking into this Project Raijin and UXarray. Moving on. So there was the very similar motivations, the arrival of kilometer scale global models, and for the time's sake, I will be really fast on a number of these slides because I think both Brians did a great job on motivating us on the kilometer scale global models already. But in general, supporting MPAS like Voronoi tessellations and CAM spectral elements like variable resolution cube sphere and others is part of this motivation as well. Again, Brian mentioned very well these challenges. I'd like to maybe add from a software development perspective, one thing here, it can become very complex when the time comes to developing algorithms for unstructured grids, which are straightforward for a lot longer grids. So that's also one big challenge the software development teams members are dealing with when it comes to unstructured grid software development. That said, motivations and challenges driving the Project Rygene goals. Two essential goals we have here. One is the obvious development of scalable functionality for analysis and visualization of the native unstructured grids without needing to regulate them to lot longer grids is at the core of the Project Rygene or UXarray. While doing this, ensuring a community ownership around this for the sustainability, long-term sustainability of the software tool, so the community can benefit from it and also even contribute to it for their expanding needs as well. For, I think, hitting both of these targets, we have centered our software development efforts around the Pangeo ecosystem of software tools, where you can count Xarray for data input-output handling and Dask for distribution purposes, and also Jupyter Stack for documentation for the community. This diagram is pretty crowded, but I'd like to highlight a number of parts on this one to deliver you the most vital information from this one. I think the part on the top section is really important. That's what UXarray does and tries to expand in the future as well. We have support for several unstructured grid models and grid file formats. UGrid, Script, and Exodus as the file formats, and not only MPAS and CAM spectral elements, which is what we have been heavily supporting from the day first. We have been also supporting and expanding our support for several other global and outside NCAR models as well, including these. And one of the most recent ones we have added into the UXarray stack as support is the HealPix from the hackathon as well. Not only unstructured grids, for data and model intercomparison purposes, we have support for structured grids and point cloud data as well. So that's one vital bit of information. Another thing, again, I'm not going to jump into a lot of the technicality here, but this is really important as well. As I mentioned before, we want our functionality to be operatable on native unstructured grids rather than requiring the user to regulate them to structured grids, even though we are acknowledging there are still use cases where regulating is going to be part of the workflows, like model intercomparison and things like that, which I will be talking about too. Just to give you a sense of how a UXarray workflow can feel very familiar with the Xarray workflows, which is very widely used by our community. So I think dataset opening is very close to an Xarray counterpart, with the exception of we have grid files and we have history or data files. Then the rest might be either the direct use of Xarray built-in functions, which can be applicable to unstructured grids as well, from maybe a statistics perspective or things similar, or we are overriding some of them to make them actually properly working on unstructured grids. And also there are functionality that we have been adding into UXarray which are not in the Xarray API. So if you have been familiar with Xarray for several years, you shouldn't be feeling any distance to UXarray workflows as well. some more on the data loading steps, which I would really like to skip. This and plotting workflows resemble very well the Xarray workflows too. Not only the function signatures, but also the end results, because we also support Matplotlib plus interactive HoloViz visualization stack. That said, I think the workflows you have already existing for your maybe structured or some other unstructured grid workflows for in an Xarray usage manner. So I think you should be able to transition or try UXarray immediately on your workflows, existing workflows easily. So to build the UXarray community is the second essential goal. In addition to what any open source software development team could do, like having our open source code on GitHub and having in place continuous integration development infrastructure, we have socialized our major design decisions and roadmap with the community as well, the end user community and community of contributors through GitHub issues and discussions, which resulted in this current view of UXarray. This is to give you a snapshot of what is the most recent version of UXarray looking like from a functionality perspective. So we have mentioned, well, the supported model outputs and file formats already. Regarding grid manipulations, you have subsetting features, and we have also remapping, basic remapping features, which is also a work in progress for added functionality here, which I will be talking about in a minute. We have cross sections as well, as you can see one of the examples here. Also, computational operators wise, non-conservative zonal means was one of the top ranked like user requests, which we put into the release recently. So other than conservative, so you should be able to do zonal means in a non-conservative way. And also we have functionality like gradients and integration, which would probably be need to improve as well, but as a significant set of initial functionality, we have these there. And also plotting wise, I think we have several visualization functions already you can run using Matplotlib or interactive HoloViz tool stack. And this is an output from non-conservative zonal mean. And maybe most importantly, if you used UXarray, let's say with the December version or one older version, you would be amazed with how things have been optimized in the most recent versions since the beginning of 2025. So check them, and some of them, like for example, phase bounds calculations and zonal means, there are 50 to 100 times optimization there, from like 200 seconds to few seconds for some of those fine resolution data sets like the 3.75 kilometers. And we have also been working on further performance optimizations for the upcoming hackathon, and also to ensure UXarray is practically usable for a number of functionality. These are all UXarray generated visualizations, from spectral elements to MPass, from data visualizations to grid topology visualizations as well. This is from diamond data that Falco had provided us with. This is also another, I think, MPass, as far as I can remember, and you can see dual and MPass primal meshes. This is a further look into how those MPass cells would look like with a 3.75 kilometer data within the UXarray visualization stack. We talk about a lot of these, but yeah, we have CI/CD infrastructure running for our development stack, and we have also, we believe we have a good, clear documentation website, but if there is any feedback, we would really appreciate hearing those kind of feedback, like, hey, your installation instructions are really messed up and things like that. So just, you know, just let us know. from time to time, we are hearing these kind of feedback, but again, we are happy to work on anything feedback-based. What else? Future work is really important that I'd like to emphasize as well. Derivatives, I had mentioned before. Our current version of derivatives is away from being generalized to broader applications, and also we don't have support for vectors in our data structure. So we are going to work on derivatives and gradients through our SciParks internship this summer with a grad student intern that we will have soon in the team. Also, conservative zonal means is what we are currently working on in UXarray. Bilinear remapping is a work in progress, which is, I think, the closest to be released. Maybe in April version, or really soon, you will be seeing bilinear remapping as well. In the longer term, we have submitted a CSSI proposal for the future sustainability of UXarray, where we want UXarray to be appealing to other science application fields too, and also become a go-to tool for unstructured grid analysis and visualizations for scientific workflows. Also, with our SciParks intern, we will be working on other analysis operators as well. Plotting-wise, we are working on some advanced plotting like contours and vectors for stream analysis for UXarray, and more gridding can be worked if needed too. But there are some discussions there if we should be maybe sticking to some existing libraries like ESMF, or if UXarray should itself look into further regrading functionalities. Future science applications that UXarray might be of help to support would be model and observational data intercomparisons because of support for structured grids, point cloud data, and also several unstructured grids. Diagnostic framework workflows would be another area that we would be help. And also coupled processes can be something that UXarray might be helping with, like ocean and atmospheric applications. And also publication quality and interactive visualizations is the area we are looking into improve in the future too. Some possible scenarios that I can think of might be where UXarray with the existing functions can be of immediate help for any scientific workflows, or maybe combining UXarray foundational functions that are aware of the grid topology with some other intermediary tools like GeoCAD-Comp and things like that, and then getting them all benefiting to some diagnostic frameworks and other scientific workflows might be also of interest in the future. Also, UXarray being, as I mentioned before, being substituted into existing Xarray workflows, and see if there are gaps that we should bridge further to make those kind of workflow transitions more convenient for the community is another area we would really be happy to look into. I'd like to talk really quick on our community engagement activities. So when it comes to advanced documentation purposes, rather than dumping everything documentation into UXarray hosted resources, we are partnering with the Project Pythia and putting together cookbooks for advanced workflows. And I think personally, this is a great way of putting together some advanced workflows about any model output or software development toolkit as well. So this is one of the existing cookbooks, which is about visualizing several unstructured grids using UXarray. So I would like to recommend to check that out. Both Brian's did make a lot of words on a global hackathon that is upcoming. So I'd like to recommend you to go ahead and register if you haven't done so. And also I'd like to give you a little bit more insights on, so we will have several science breakout rooms for this hackathon at the local Anchor node. And we will be able to have multiple GeoCAD and UXarray folks present there within those breakout rooms. So I would really like to have our team members to get a sense of end-to-end scientific workflows so that they can better understand the community needs, and also that all of those people would be of help for UXarray or other tooling needs or anything else about Python and Conda and things like that during the hackathon, throughout the hackathon as well. Some other community activities that or engagements that we are having is Christian Jablonowski's DCMIP is one of them that UXarray has been exchanging some emails about and supporting some of the visualization things. There are more we will be doing there. Also some engagements with other labs, Earth System Science and Earth System Data Science. Co-working times were one of them that we did in the past and turned out to be very effective for the scientific and development community. Also, we have been exchanging ideas and maybe looking to future collaborations with CGD's Cupids. MCubes and Pass Workshop is also one of those annual events that we have been part of with our talks and tutorials. Also, I forgot to mention here, but Earthworks and SEMA folks that we did have discussions before was all helpful for us to understand better the community needs and look forward to development of UXarray functionality. So that's everything. So thank you so much, and please let me know if you have any questions.
Actually, if you want to wear one of those, yeah, I'll go around for this. We'll start with Fred, then I'll come to you.
I don't think we need that.
Oh, it's the ceiling mic's on. Okay, yeah. Fred?
So, quick question, is UX, nice tool, thank you. It's, I think, a very exciting new capability that will be very useful for a lot of people. Is UXarray available in the latest like NPL library?
Yeah,
Great.
that's a great question. Thank you so much. Yeah, I think I should improve my slides. Yeah, since the NPL 2024A, UXarray has been part of them. For this upcoming hackathon, we will have a dedicated Conda environment. Is the audio good?
I think they're just using
The ceiling mics. Ceiling mics are on already.
So you don't need to worry about it.
Yeah, I don't need this either. Okay. Yeah, like for the hackathon, we will have a dedicated Conda environment for the event itself. Regarding NPL environments, we have been part of NPL since 2024A. Again, I would highly recommend to use the most recent one because the older ones would give you really bad impressions about UXarray that you would be really annoyed about. So performance was not that good. So I would highly recommend. With 2025A though, there were some things with task and related packages. So we are exchanging some information with the CSG folks there. If there are any issues, again, reach out to any of you from UXarray or maybe CSG or NHub. We can get the things up and running for you.
I'll add to that too, that by way of example, I upgraded after using an old one, and it went from, I don't know if it was 30 minutes or so to read in some grid data to like 2 minutes. And this is at the 3.75 kilometer grid. So it's really fast. It did a lot of great stuff. We have a notebook we can share for that we used for doing animation of some early 3.75 kilometer work, and UXarray worked flawlessly. It was really nice. So yeah.
Thanks, man.
Sam?
When you're using UXarray to read in a regular grid, you still need to provide that grid file?
No, in that case, no, we wouldn't. And we are providing a special API for that one, which is not open dataset, because it will be really confusing for the end user. It is from structured. When you call from structured, which can take only one data file or multiple data files, rather than asking you to put any grid file. And we have documentation about that, I can show that to you.
Let's go with Azusa first.
Yeah, I have a question to Brian Medeiros. I was wondering if you can comment on the vertical resolution, if the kilometer scale global simulations have like maybe hundreds of vertical levels, or they're more or less the same as like normal, usual global simulations.
So far, all of the in-car ones use a normal vertical grid, so it's the same vertical grid as you go down from 100 kilometers down to 3.75 kilometers. There are a number of different vertical grids that have been used, but they're all the same. They're the same across horizontal resolutions. For the diamond models, I think some of them might have special, like custom vertical grids, but I'm not really sure. They're not that different from weather or climate models, though.
Hey, Adam, if you don't mind, I'd like to add to the structure grid one other thing. So regarding the structure grids, so we are not using the hierarchy coming from the lot and loan. Instead, we are representing the structure grids in the same, like per grid cell structure, right? So because of that, there might be some performance optimizations needed in the future, and I would be really happy to hear folks' perspective on that one. Not right now, but in the longer term, right? So we would like to hear if there is things that can be done there. So we would like to do those kind of improvements as well. Adam, what's next?
Oh, is Adam next? Sorry. Yeah,
I think so, yeah. I'm not sure, yeah.
There's a lot of people have questions, but I have a question, Orhan, about your thoughts about user accessibility to grid files. So in CSM, all the grids that we have, we maintain in our CSM input data repository.
Mm-hmm.
However, the average user does not know that, nor do they know what grid file to be looking for.
Mm-hmm.
And so I wonder if you've thought about, is that kind of just not your problem, which is understandable. I feel like models should, for example, in our metadata and our output, history output, have a path to the grid file, but we don't currently do that.
I see, yeah.
So I'm wondering if you have any thoughts just generally about that issue.
Yeah. From my own understanding, it looks like a natural part of unstructured grids. So what can be done there, in addition to how we are reading in those grid files? Maybe embedding them into data files, history files might be an option, but I'm hearing from people it may not be practical in a lot of cases as well. So I think this is a natural result of having grid topology defined in separate files and a software tool being required to understand the grid topology. But again, if there are ideas there, it would be really helpful to further discuss and see if there are things that we could do. We would definitely do. Is that a good answer to your question?
Yeah, I mean, in terms of things that you could do, I've thought about could we develop a tool that generates these grid files? But that seems hard to generalize. There's just so many different geometries out there.
Yeah.
So that's a thought, but I don't know whether it's something worth.
Adam, I might add that because we have a limited number of geometries that we typically use outside of the regional refined, I can think of a couple of ways that we could do this as well. I think it's just, it hasn't been a focus point yet because we haven't gotten to that point where this has been our shift. But there's a number of things that we can work together to address. The other thing is I'd also love an indirect thing so we don't have a different read for the structured versus unstructured.
Yeah.
But we can solve all that. That's all doable. So, yeah.
Also,
I think,
Go ahead.
That's the idea of getting all the CISL and CGD side together. I think, it's reached the point where it's mature, we've used it for things. Now we just need to bring in the needs from CGD and the expertise from CISL, and we can kind of get there.
Yeah, and when I'm saying we are socializing these kind of requests, it is not only a presentation kind of thing. So please, if you have any thoughts, maybe go ahead and put your thoughts into one of our GitHub discussions. Create one. We can further the discussion from there as well. If we don't have, chance to come together from the person. I don't know, Brian, please moderate the.
No, I'll let you call on people. I'll just keep an eye on time. Yeah. I don't want to make people late for lunch. Yeah.
You mentioned expanding this to other geoscience areas. I see that ESMF mesh is supported, and all the components in CSM all have a ESMF mesh. Are we ready to, for example, trying to load the ocean mesh or ice sheet mesh and see if the tool will work, or this will be a waste of time at this moment.
We would really need to know the maybe grid file format there that you are using, so it would really be, but it would be really convenient to just go ahead and try UXarray, and we can give you some feedback on, hey, we are looking for this and this, but we are not being able to read from your files and things like that. We can definitely check on those kind of things. If you want, provide us with some pointers to some of your data files. We are happy to look into it.
Yeah, Gustavo, I'll add that we're hoping to do some work on the ESMF side soon to also expand the command line capabilities there and the Python interface, because even the command line tools for ESMF don't read the ESMF meshes, I think, correctly. Bob can correct, or it's
No, they read it
it's
correctly.
which one is the one that we're trying to fix? Yeah, but there's some improvements here we're going to make. Yeah.
ESMF regrid that does,
regrid.
they will do regridding without generating the weight files.
Right. So I think it's just a matter of expanding the
support
ESMF
strip
mesh
files,
stuff
Yeah.
into this.
And as part of the upcoming hackathon, yeah, there are going to be some like themed subjects for each of the breakout rooms, but at the same time, we will be asking people to bring their breakout room ideas as well. So if you have data that you would like to try out with UXarray, please maybe consider coming there, and we can definitely look into it with some of our developers.
More questions everywhere, yeah.
Yeah, I was wondering, in the improvements to derivatives and integrals, is that proceeding in a grid-specific format, like understanding the numerics of the grid, and are there things in model output that would make it easier to do this kind of work?
That's a good question. I think I would need to maybe double check this from our implementation, but to give you some insights into our implementation, it is the first versions of our implementation regarding, for example, gradients. We collaborated with one MPass MQ postdoc who worked on solely MPass, and the implementation was also solely for MPass. We tried our best to generalize it as much as we can, but there is going to be a lot to do there for generalizing that to other like broader applications as well.
Yeah.
So would we be looking into some model-specific things? Maybe, I'm not sure. So we can definitely, discuss, and if we feel there's going to be, benefits for the community's use for those kind of additions, we can look into it.
Let's get, Judith has one online too.
Oh, okay.
Let's take
For
that
Ryan?
first.
Yeah, so there has been some success with developing emulators for kilometer scale models. The examples that I know about are mostly from Chris Brotherton and his colleagues, both when he was at UW and now at the Allen Institute. They've done emulators of a near global aquaplanet and also the GFDL X Shield simulations. And I think they've had pretty good success. I imagine that there are other examples too that I don't know about. Maybe other people do.
Dan, yeah.
Brian, you noted the 70 million core hours per year.
71.
71. Even worse. In terms of getting us to a point where we can use, kilometer scale models to do science, what role do you all see for regional models as a way to really cut those costs?
I mean, well, you're asking me, and I'm the software guy. I think that's more of a science question. I feel that regional models is where we're going to see an explosion in use because the global uniform are so expensive, but the regionally refined will still let us do scale-aware parameterizations and develop the models and look at phenomena in more detail. But I would defer to Brian Medeiros on all of this.
From my perspective, I think what we'll see is we'll see a number of applications that use the global kilometer scale, but I think we're still limited in terms of like length of runs. Like that's just not going to grow very fast. But the regionally refined configurations and then regional models themselves provide a bit of a hierarchy that we can use, I think, to our advantage. So the regionally refined in particular, I'm interested in because they give at least the possibility of having consistent physics across the entire globe. So you don't have to have lateral boundary condition issues as much as you have in regional models. But the regional models have had a lot of exercise in being run on continental scale, long-term simulations, which I think will be useful and maybe become more useful going forward.
I have a question for Brian Dobbins. The numbers were really interesting, but I didn't see the throughput factor. Do you know what that is?
Sure. So on this run right now on 38,400 cores with the undersubscribed nodes, we're getting about 4.9 simulated days per day. You know, it's an improvement over what we did before, but it's still got a ways to go. We have run actually, I should say, we stopped with the full runs at around 40,000 cores. There's another interesting problem you get when you go above. It sounds odd, 55,296 cores, and you might be like, well, why is that? And that's 192 by 288. When we remap some of our input files from the FE 1 degree case, nobody anticipated having more cores than you had points to interpolate from. But when we used an aquaplanet run, we did run out to half of derecho on 164,000 cores using 1,280 nodes, 128 cores per node. I don't remember the throughput of that, but it scaled linearly as well. So yeah, it was pretty impressive. We'd love to do that more. I'd also just love a bigger system, but yeah, we'll see.
Do you know the factor though? Because you were listing factors.
Right. I didn't check the simulated years per day we were getting on the 1 degree. I can probably get that for you right afterwards. But since we're super linear, it would be, you know, it would be efficient. It would be 29,000. That was the time. So 29,600 times slower. So yeah, well, scaled by the number of nodes, the resources. That was the cost. So scaled by the number of nodes, and then you get that. So yeah, I can tell you that after if you like. Yeah.
This is more a general question. Given the scale of which, you know, these high resolution runs, the computation requests and everything else, is it sort of sensible to have 3, like Earthworks, SEMA, and MPAS, all independently being developed so that you're having to run 3 times the number of simulations? And
this is a great question. I think that the areas that they focus on are different. So Earthworks has done some great work on GPUizing the physics. And they want to run, of course, with the MPAS, sea ice, and ocean. But that their work has overlapped with the SEMA work and the CSM work that enabled some of these runs. So they're different. Storm speed is a really interesting one because it will still use, like, all the benefits I showed of the ESMF infrastructure, the PIO, those are all reused. The spectral element die core is really interesting because when you look at the number of physics columns you have, DOE runs it with a PG2 physics grid, and that means they have 24 million physics columns versus 42 million in the CAM-MPAS. So the physics might be much faster, and that might also be cheaper. Whether it's accurate, I'll leave that to the scientists. You know, but there's a lot of overlap. We like having multiple capabilities because it could be that some are better for other purposes, and yeah. But it's not a duplication of effort across each project. We, in fact, there's a regular meeting every 2 weeks where we all talk and update each other. So it's a lot of collaboration there, yeah. We're really out of time. I'll take 1 or 2 more. Yeah, John.
Yes, I just have a quick comment.
Yeah.
So the hackathon that Brian, and Orhan had mentioned, that's the WCRP Digital Earth Global Hackathon. Registration closes for that next Wednesday. So hope to see many of you there. If you have any trouble finding information about it, Brian or Orhan can point you in the right place. But again, next Wednesday, 23rd, registration closes.
Yeah, and I'll just emphasize that we'd love for people in CGD who are working on diagnostics to find some time because you have the experts from CISL, especially if you're not familiar with UXarray. It's a great chance to learn it. I, again, see this as a potential for us to unify our approach so that we can, in the future, do comparisons between SE and MPAS runs or MPAS and FB runs, all in the same notebook. Like you know, our notebooks, our diagnostics take a lot of time to develop. If we can do it in one way, that would be ideal. So, yeah.
So if we run out of space, because we have limited space at Foothills,
sure.
I'm sure that we can find ways to
satellite,
get satellite nodes set up or something.
Great. Any last questions? Otherwise, I'll let people go to lunch. Great. Well, thank you very much. Come ask us. Yeah, thank you. That was great. Yeah.